So, we're going to get started today. I do apologize. I'm a little scattered. I didn't have time to prepare. I started getting set up. Because some piece of trash, some human dumpster fire, I don't know. Someone, and we figured out it was injured after, took a cat and put it in a cardboard box, a tiny cardboard box with a towel, stuffed it in there, and just left it at the door to the ST hall, outside, in the cold. So Mr. Shilley and I get to school at about the same time. We found it out there. It's still in the golf room. We put it in the golf room. We don't know. I think some teachers might take it home. I don't know. But it's got an injured mouth. It got injured, and so they probably didn't want to take it to the vet, so they just dumped it here. They just dumped it. Are you raising your hand because it was you? Because that'll make me upset.
Not exactly.
Okay, good.
I really thought you were going to say some human piece of garbage named Trenton.
Yeah, that's
No. That would be terrible. No, I reserve words like that for people that, abuse animals in such a way. So,
And Trenton abuses animals, you know that, right?
Trenton, you don't abuse animals, do you?
No.
Okay, good.
Well, suspicious.
All right. Oh, wait, let me see. Oh my gosh, that's adorable. Okay. All right, it wasn't Trenton. I don't believe it was Trenton. Okay, so that being said, that ate up. I got here about 6 with an hour and a half to get ready, and that ate up most of that hour and a half. And so I might not do that great today.
What did you name the kitten, or is it a cat?
It's a cat. It's not. It looks pretty young, but it's not a newborn at least.
What did you name it?
I didn't.
Oh,
Mr. Shilley and I were both in a terrible rush, so we just Miss Cook, Miss Ensley, she's an animal lover. If you don't know, you probably know. So I texted her because I knew she'd know what to do, and she brought wet and dry food, a bowl for water, a portable litter box. So it's hooked up in there right now. That's Miss Ensley for you. Okay. All right, so let's get started. So last week we started our new unit, electric potential. By the way, there is homework tonight. It is not a quest assignment. The homework is because I'm going to explain some things. Mr. Fullerton is going to elaborate on some of those and then tell you how you can get electric field expressions from potential energy expressions. You can get voltage expressions from electric field expressions. So there's various ways of going about doing that. I will have a set of notes as soon as possible. I was going to try to get those into the copy lady this morning as well, but I wasn't able to. So I'll have a set of notes for electric potential for you. But you do have to watch the video. There's a few questions at the end that are real basic and real easy to answer as long as you have watched the video. So please do that. That is a homework assignment.
Homework is to stick a fork inside of an outlet.
Only for you.
Yeah.
Only for you, Connor. Okay. So what we talked about last week is that when we take a charge big Q and say keep it fixed, and then we bring another charge little q, or just other q, in from infinity, meaning from kind of far away, to some position r, then that object obviously will have potential energy, right? Electric potential energy. And if I were just to let go of him, then he just springs off because we have a repulsive force, and so that object will fly away, gaining kinetic energy while it loses potential energy. Just like when you stretch a spring. When I pull a spring back, come on. I pull this guy on the spring potential energy starts turning to kinetic energy. Same thing. I bring a charge in, I store electric potential energy, I let go of it, that potential energy becomes kinetic energy. And so, just so you know, you can do conservation of energy problems with this, right? So the electric potential energy is the work done in bringing that charge to that location, and that is K, in this case, big Q, little q, over R. We showed that on Friday. How do we get that? Well, we calculated the work done to bring the charge to that location. And then that work is just the amount of potential energy. And then we said Well, we can talk. It's not potential energy. Like I want to be able to describe because at this point I can talk about the potential energy stored by that particular charge that lies within this electric field. But what if I want to talk about any point in space around this larger charge, big Q, and I don't want to have a charge there? Well, then I'm not talking about potential energy actually possessed by particles. I want to talk about the electric potential in that space. Just like an electric field allows us to talk about the amount of force per unit of charge that exists in space surrounding a charge. That is a vector field. I can also talk about the potential field or the electric potential scalar field that surrounds an object or a charge. And then so we just said that, well, that V, it's voltage, right? That's what electric potential is. Its voltage is the electrical potential energy per unit of charge. Okay? And so on the formula sheet, electric potential energy, electric potential, and the actual expression to calculate them are related in this way. The electric potential energy equals charge times voltage times electric potential, which equals K, I know, is also 1 over 4 pi epsilon naught times Q1, Q2 over R. This is how electric potential energy and electric potential are given on the formula sheets. Cool beans?
Charge beams. A difference in charge, that way there's electric potential.
Yes, sir.
So do they get that equation on the equation sheet from kind of plugging that U of V equation into that voltage equation, and then you just kind of the Q's cancel out the little Q's.
Yeah. Mm-hmm. Yeah, it's all about that little q, right? If I divide this by little q, then I'm essentially dividing both sides of this equation by little q, and then giving this the name voltage, right? And then this is electric potential energy divided by charge. Right? Yeah. Astute observation.
Gracias.
Opinion. All right. Some other stuff that I'm not going to get too into some of this other stuff because Mr. Fullerton will, and because I'm just scattered right now because I didn't have the time that I wanted to prepare this morning. Notice if you're doing a conservation of energy, let's say we put this charge here, a distance r from big Q, and then I let go of it. And the question says, how fast is it moving after a certain amount of time? Or after it moves a certain distance, how fast is it moving? Well, I just have initial electric potential energy, and then a final electric potential energy, and a final kinetic energy. And I just do conservation of energy. And I can do conservation of energy because the electric force is a conservative force. And so conservation of mechanical energy will be valid. Okay? That Mr. Fullerton will go over. Wait, I feel like I'm missing something. I'm sorry, guys. This is terrible. Collection of point charges. Mr. Fullerton will go over that. One thing I do want to emphasize again. The electric force is equal to the negative derivative of the potential energy with respect to position. Any conservative force can be written in terms of the derivative of the potential energy associated with that conservative force with respect to position. That comes in handy sometimes. All right. So let's talk about something kind of fun. Oh, and the other equation. This isn't on the formula sheet because I emphasized last week, it's not the electric potential that's really important. It's the electric potential difference that's really important. But what we did see, I think we saw this. What we did see is that the voltage is equal to the integral from R, position R, where the charge is actually located, to infinity of the electric field dotted with dr. So that's another big takeaway point that we got last time. This isn't going to be the important equation on the formula sheet, though. You'll see something if you look on the formula sheet that looks similar, but what's on the formula sheet is actually going to talk about the delta V, the potential difference, because that's what drives current. That's what drives electrodynamics, right? Just having an electric potential, I'll turn on the Van de Graaff generator over there, and there will be electric potential surrounding it, but nothing will happen. Right? You need to have a potential difference, and then something else in order for electrons, for electric charge to actually flow. Okay. All right, so let's talk about the Van de Graaff generator then, real quick. Right. Yeah. Oh, I gotta do the camera. Oh.
So the differential of voltage with respect to position would be the electric field then, right?
Yeah. Yeah. And I think that's not on the formula sheet, but yes. That's something we'll definitely get to as well. I think Mr. Fullerton will talk quite a bit about that in his video. Oh my gosh. Okay, my camera in class, for those at home, is on an angle. So yeah, this demo is going to be on a Dutch angle for those filmmakers in here. You know what Dutch angle is? Of course you do.
An angle from Deutschland.
From Deutschland. Okay. Again, I apologize. This is terrible. Today's not my day. Okay.
Today doesn't count.
Well, kind of counts because I am going over stuff that you need to know.
It's Friday somewhere.
That's right. Is it? I don't think it is. Okay. Oh my gosh. So you guys have seen these before, right? We'll mess around with this in a little more in coming days, but this is a Van de Graaff generator. That was working great this morning. Oh, there you go. You've seen these, right? So there you got charge actually flowing, but when you do this, nothing. What's that? Second?
Is it gonna be attracted to the cabinet surface?
It'll put some shocks there.
Go ahead.
There you go.
I'm kind of saying.
Yeah, it's small. Get bigger ones on this guy. Woo. Okay. So, how does this work? I don't even remember if I showed you guys this or not. Let me,
I could
Did
feel
I
static from over here and it was kind of scary.
Can you?
Yeah.
So yeah, that's the electric field that you're sensing, right? So did I show you the tape trick?
Where you rip them apart?
Yeah.
Yeah, you showed us that to introduce static.
Okay, good. So, come on.
Now I notice that every time I rip something apart and then it's like, oh, I got that.
So if I have these two pieces of tape that are stuck together, they're different surfaces in contact. I got a sticky side and then the smooth side, and I rip them apart.
Oh no.
And then I ruin it. So now they're oppositely charged, and so I should get an attractive force. And I do get one, right? Even if I flip them around, I get an attractive force. So that's because by making physical contact, you don't have to, like, we use the rabbit for, oh man. I didn't see that at home. Their fault.
It's your fault
We're getting quarantined. Those at home, this is what I just did. I have two pieces of tape that I stuck together and then ripped them apart, and charges got taken off of one and deposited on the other, and so I get an attractive force. Right. Even if I turn them around the other way, there's still an attractive force between them. So, usually, in demonstrations, we take rabbit fur and rub it on like acrylic or polyethylene or rubber or something like that. And it'll actually take charge off of the stuff and put it onto the rabbit fur. I think rabbit fur gives off electrons. These work on the same way, the same basic principle. It's just a hollow metal dome, and then I think it's a PVC spool with a rubber belt on it. And all it does is roll. All it does is roll, and so as it rolls up, the belt, it comes into contact here, and then it breaks contact there. And when it breaks contact, electrons are transferred from one to the other. Usually, it's the rubber belt taking electrons from the spool. And then the spool gets recharged from the dome. And so electrons are continually taken away from the dome, put onto the spool, and then the rubber, whenever it breaks off of the spool, will actually carry some of those electrons with it, just like you get a transfer of electrons whenever you rip the tape apart. Okay? And so that's how the Van de Graaff gets charged. Most Van de Graaff generators become positively charged. Okay? So that means they're deficient in electrons. And when you charge this guy, let's assume it's spherical, then it builds up a total amount of charge on the dome. All of that charge, is good, because it is a kind of a spherical shell, but there is dimension to that, and so we know that excess charge goes to the surface. It all goes to the surface, creating an electric field of what inside the ball? Zero. Yeah. So inside the sphere will be an electric field of 0. In reality, it's not going to be exactly 0 because you got like a big hole in the bottom, and you got some other stuff, but it's close to 0. And so we know how to deal with the electric field for that, but we want to know how to deal with the electric potential as well. And just to give you an idea as to why potential difference is the most important thing, or is the important thing. When I turn this guy on, here I got one of these bulbs. You guys ever seen the emission bulbs, where you look at them with the spectrometer and you can see the spectral lines?
No.
Yeah, you should have done that in like 8th grade science.
Well, go yell at
My bad.
Mr. Left.
I will.
Mr. Boom.
So I'm going to hold it. I'm going to do my best to hold it like this, to where each end of the bulb is equidistant from the sphere, so they'll be at the same electric potential, right? So there won't be a potential difference. And then I'm going to move it like this, so that they're not equidistant, and so there will be an electric potential difference, because it's KQ over R, right? KQ over K times Q on this, divided by the distance from this. So this is farther distance, smaller potential, higher potential. Okay. And so whenever they're approximately the same potential, stop moving. Then nothing really happens. But if I move it so they're at different potentials, then I start to see stuff happen. See it? So because they're at different electric potentials, there's different electric potential energy per unit charge. It's kind of like charges rolling downhill, right? This is the high top of the hill, this is the bottom of the hill. Whenever they're equidistant, they don't do anything, right? But it's when they turn, right? When they turn. He's acting up today. Anyway, you see what I'm trying to get at, right? We'll play with this guy a lot more in the future. You guys know how these work? There's gas in there. There's no wiring going from one side to the other.
Oh, is it like helium or neon or something?
This one is neon, I think.
Okay.
Yeah, that's the actual color of
There's
neon.
the red.
And neon has a specific color. It's not like all colors are neon. Okay. So let's talk about the Van de Graaff generator. Let's consider it to be charged. Again, we'll do more experiments with that in the future. Oop, not that way. Nope. Stop it. Stop it.
Hello.
It's pointing too high. I didn't see any of you. It might have seen your hand. I don't know. Oh, it was zoomed in. That's why. Okay. So that potential difference that I was trying to show, that's the version of this that you'll see on the formula sheet. It doesn't have the limits of integration on the formula sheet, but the limits of integration will be very important. And it does have a delta in front of the v. So don't worry about that yet. We'll talk about that later on after the video from Mr. Fullerton tonight. Okay. Let's talk about the Van de Graaff generator. So let's say this is the Van de Graaff generator. Electrons have been stripped off of it. So we have a net positive charge on the surface. And that charge is all spread out equidistant from all the other ones. And I'll just say the radius of the Van de Graaff generator. Let's assume it is spherical as capital R. And we know that inside the electric field is zero. And obviously outside the electric field just points radially away in all directions, and that vector field fills the space outside of it. But remember, we have also shown that outside of R, it just behaves like a point charge, right? Right off the surface of the Van de Graaff generator, as far as electric potentials and electric fields go, we could just assume that all that charge is concentrated right there in the center, and it works exactly the same way. And we know that that electric potential as a function of position is simply 1 over 4 pi epsilon naught times the charge responsible for the potential divided by the distance. You probably just want to think of it as KQ over R, right? But usually on formula sheets, it's written in terms of the 4 pi epsilon naught.
Is the reason why it's delta V on delta V on the formula sheet is because you need a difference in voltage for there to be any difference?
Yeah.
Okay.
And so just calculating because the electric potential is related to the work done in bringing a test charge, an imaginary charge, from infinity to that location. But the potential difference will be, well, the amount of work required to take a charge from one end of the tube to the other end of the tube, not far away. Yeah. We'll get to that probably tomorrow, once I've had more time to plan stuff. Okay. So let's say we want to plot the electric potential V as a function of distance from the center of my charge here. Now outside, and we'll draw the graph over here, electric potential and position. So outside, the outside outside R, which just means R is greater than capital R, because capital R is the radius. This is the expression, right? So if I go to R and I go outside of it, what type of relationship do I have between potential and distance? Inverse. And immediately off the surface, an infinitesimally small distance off the surface, this is the expression for that potential, but I have capital R here. Right? So the potential at that point will be 1 over 4 pi epsilon naught times charge big Q over big R. And so at that point, it starts behaving like an inverse, or it has an inverse relationship. If this was electric field, this would be similar, but it would be proportional to 1 over R squared. So it would hug the axis a little tighter, right? If it was electric field, it would be 0 up until R. What do you think the electric potential inside of the Van de Graaff generator behaves like?
Negative?
Someone say 0?
No, it's about to.
no electric
Negative?
field inside, so.
Negative K Q over R.
There's no electric field inside. That's the key.
Constant.
0 dot du.
Constant because dV over dr is the electric field, and if the electric field is 0, then it's constant.
It's constant. It's not zero. And think of it this way. If you're not as far ahead as Logan, the integral of E dot d r, electric field is 0. This is just the integral of 0. What's the integral of 0? That's literally the reason why you put plus c at the end of every indefinite integral. Because you have to integrate the 0 that comes along with it as well. Because the derivative of the 0, or the derivative of the constant is 0. So going backwards is constant. And so it's actually constant. And what that means is that it takes no work to move charges around in regions of 0 electric field. Right? As long as you ignore their mass. If you consider them to be massless particles, I can move charges within positive or negative because the electric field is 0 and it takes no work. It's like sliding an object around on the surface of my table here. That I can move it around on the surface of the table. The gravitational potential energy, the gravitational potential doesn't change. And so it's easy to do that. I don't have to lift against it, right? It only starts to fall whenever I push it off the edge of the table. So it's like moving a charge around inside of a charged conductor where the electric field inside is 0 is like moving something around on the surface of a table. But then as soon as you get outside of it, it's like pushing it off the table. It's now going to start accelerating. Okay? So it actually would look like this. Good job, person that wasn't here Friday. So it's kind of like the electric field relationship, but the electric field is going to be 0. And then we got to,
I guess the constant is just KQ over R.
Yeah. So here's an interesting little. Again, I would have been more ready for today if it wasn't for the cat. Not the stupid cat. The stupid human. It turns out that this Van de Graaff generator has a radius of about 15 centimeters. And your typical Van de Graaff generator can store about 2 microcoulombs of charge. So when you see, those at home, I'm shocking myself with the Van de Graaff generator, that's it. So when you see the Van de Graaff generator shock me, hello?
Whenever you see a construct,
Oh, there you go.
concept.
So when this is fully charged, that's about 2 microcoulombs of charge. Shocking. People with their weak side use this. So that's about 2 microcoulombs of charge. So 2 microcoulombs. So if we know that this is the expression for the electric potential, both right at the surface, but then also inside, let's actually determine what that voltage is. What is the voltage on the surface of the Van de Graaff generator? Well, we know it's going to be, and I'm just going to use K because I know that off the top of my head. K times the charge Q, which is 2 microcoulombs, divided by the distance, 15 centimeters, 0.15 meters. Right? Sorry, distance, capital R. So that's my potential, KQ over R. Let's work it out. This is about 9 times 10 to the 9th. Charge is 2 times 10 to the negative 6th. Divided by 0.15. Gianni, what's that? You can do that in your head, right? What am I looking around for? I have this on my notes. This comes out to approximately 120,000 volts. And this is one of the major areas of mental confusion for a lot of students. Because, how many volts, does anyone know what the volts on the outlets in the wall are? What? 120. 120 volts, the outlet there. And if you're like Connor, you're going to go home tonight and you're going to stick a fork in the outlet and you're going to have a bad day. Okay? You can definitely die. Don't do that on the record. Don't do that. You don't want to do that. You can die. The electricity out of the outlets in the wall can kill you. That's 120 volts. This is literally 1,000 times bigger. 1,000 times more volts on the surface of the Van de Graaff generator. Yet I touch it and it doesn't hurt. Some people are a little squeamish. Ooh, it stings. It's not that bad. But I can do that with complete confidence that I'm not going to be hurt. And the key to understanding why is the whole per unit of charge. You really want to get that in your brain. Per unit of charge. The electric potential is a measure of the electric potential energy per unit of charge. So all that means is that each charge on the Van de Graaff generator has a huge amount of potential energy. There's just not that much charge on it. And so the total electric potential energy is not that much, right? Whereas you plug into the wall, you have pretty much limitless available charge. And each one of those tiny charges, each one of those coulombs of charge has 120 joules of potential energy, or just electrical energy. So it's not nearly as much as each charge that's on the surface of the Van de Graaff generator, but because there are many orders of magnitude more charges in the wiring in your typical building circuit, there's just vastly more than you can store on the dome of a Van de Graaff generator. Vastly more. And so it's all per unit of charge. And I like thinking of the little sparklers. You know, you light the sparkler and it sparkles and you wave it around and you say, woo. And those sparklers are crazy hot. They're crazy hot. They're over 1,000 degrees. Those things burn over 1,000 degrees. But you can put your hand over them and let the sparks hit your hand. And as long as you don't do it on the same spot for too long, you barely feel it. Even though the sparks hitting your hand are literally at like 1,000 degrees. The reason it doesn't hurt is because, there's a lot of thermal energy per unit of mass. But there's just very little mass. So because there's very little mass, you don't get that much total energy. Yeah, you have huge amount of potential, but if you had more of that mass at that temperature, then it's going to burn you a lot. But because you barely have any mass at that crazy high potential you can think of, then it's not a big deal. So it's about the per unit of charge. Does that make sense? Did you get that? Voltage is not dangerous unless that voltage has a supply of charge.
Well, voltage isn't dangerous.
Voltage is not dangerous. A voltage can be dangerous as long as it has a supply of charge. So keep that in mind. Van de Graaff generator, 120,000 volts.
So how does the Van de Graaff generator not have a supply of charge?
Because it's when we learn about capacitance, we'll learn that spherical capacitors, which a Van de Graaff generator generally is, they're terrible at storing charge. They can, once it builds up to a maximum amount of charge, you can't put any more on it. Okay. And a dome, a spherical object. Now I can increase the capacitance. I can increase the amount of charge that it can hold just by moving another one close to it, like this. But that's something that we'll get into when we start talking about capacitance.
So that one holds a whole lot less charge than the outlet holds, and the outlet holds basically an infinite amount of charge.
Yeah, the circuitry connected to the outlet, yeah.
Oh, okay.
There's a ton of charge there, yeah. Whereas the Van de Graaff, there's just a very tiny amount on the surface that you can touch with no fear of actually, getting hurt. But then you can start storing that energy in a capacitor that you can get from the Van de Graaff generator, because while the Van de Graaff generator is on, it'll continually load it as long as you're continuously discharging it, which you can do into a storage device. That's what they did in the early experiments. The scientists would have their assistants come in the morning and throughout the day and get on stationary bikes that would essentially do what the Van de Graaff generator does to store up their capacitors so they could do their experiments. They would just ride a stationary bike and charge the stuff up. It's pretty interesting.
Next year you should say that the Van de Graaff generator, you're completely confident that it isn't dangerous, and then go and shock yourself and then act like you got hurt.
Maybe I will. Maybe I will. I did that with the laser. We have a laser here that's like it's really old, so it's in a big housing, but it's just a red laser, and so I'll be like, and they'll think that I'm really burning myself. Even though if you know anything about lasers, you know red lasers are the lowest energy ones.
Shock yourself at your head and just like pass out.
That would be mean.
It'd be funny though. You should do it on April 1st.
Well, I can't do it in here now.
That's my dog's birthday.
All right. So this is something important. Oh man, today got off on the wrong foot. I love it when that happens. Okay. So the difficulty with electric fields, Coulomb's law, Gauss's law, electric potentials, it's pretty much all invisible, right? You can see me getting shocked when I touch the Van de Graaff generator, but it's pretty much all invisible. That's the difficult part. Did I? Oh, of course I did. What? Where'd it go? Okay. I put it on the wrong one. Okay. It's all invisible. It's all invisible, and so the mathematics is what we need to use in order to actually visualize the stuff, but then we have nice simulations like this that they haven't had in previous times. So here I got charge. Whoa. Here I got positive charge. Notice if I put a negative charge, then the field lines point towards it, right? So here I have a positive charge. The white arrows indicate the electric field lines. Okay. And then what I can do, here's a voltmeter. I can come out here and it'll tell me what the voltage is at every point. So right here it's 13.3 volts. And if I hit this button, it'll draw a circle. That circle is what we call an equipotential surface. Sometimes you'll hear it as an equipotential line because it's a line. But imagine if this was three-dimensional space, it would actually be a sphere that's concentric about the actual charge. Okay. Why is it called an equipotential surface? Well, equi means equal, potential means potential, so equal potential, right? So an equipotential surface is just a surface on which all points are at the same electric potential. So charge will not freely flow from one point to another on an equipotential surface. If I draw another one, say right here, this one's at 5.5 volts. The original one was at about 13 volts. So this guy's at 13 volts, this guy's at 5 volts. If I put a positive charge here, and before we talked about voltage, if I put a positive charge here, what's it going to do? Well, no, if I place a charge that's free to move here, what's it going to do?
Okay.
It's going to move down, right, radially away. So it's actually going to move from high potential to low potential, right?
Okay.
Entropy. I don't understand entropy. The thing is, what if I start putting charges somewhere else? What if I start mucking up things by putting all this weird stuff? Is there going to be an equipotential? Or is it going to be... Oh, it gets pretty gross. So here's a bunch of equipotential surfaces. Some are negative. No, these are negative voltages now, right? Voltages can be negative. That's fine. And the thing about equipotential surfaces, if you release a charge, a positive charge, from an equipotential surface, it will spontaneously move to a lower potential. Okay. I feel like the easiest way to understand this is to make the analogy to topographic maps. You guys know what a topographic map is, right?
Yeah.
It's a map showing the topography.
That's what I was just thinking.
Yeah. This is Mount Elbert. This is the one I climbed last summer. This is on the way up Mount Elbert. So obviously you see the topography here, right? And you can show that topography on the map with lines of equal elevation. Sorry. And so you can think of these as like equipotential surfaces, but equigravitational potential surfaces. Where if you were to take a ball and just release it from one of those lines, it's going to spontaneously roll downhill. So think of charges moving from high to low potential as just moving from high to low potential, rolling downhill. Okay? That's the easiest way to understand what's going on when it comes to potential and electric potential and the motion of charges. The problem is that if you have a negative charge, what's the negative charge going to do? It's going to roll uphill. Okay? Because positive charges go from high potential to low potential. Negative charges do the exact opposite. All right. So topographic maps.
Well, would it still be from high to low? So if you had like negative 8 volts and then negative 13, would it go from 8 to 13?
Yeah, they'll go from negative 8 to negative 13. Yeah. Because
Okay.
negative 8 is a higher potential than negative 13.
Okay.
Yeah. Yep. It still works like that for sure.
Absolutely.
All right. I'll show you this tomorrow. Actually, what time are we done here?
Oh, great.
I think I actually, I might have time. You guys heard of Maxwell? He's a scientist named Maxwell. You ever heard of him?
Just Maxwell.
So, James Maxwell. Is there a teacher named Maxwell here? Yeah, he's got a silver hammer. Nobody? Connor?
I can't think of him.
Maxwell's silver hammer?
Oh, yeah.
Yeah.
I know what you're talking about.
You know, you disappointed me again.
The silver hammer and whatnot. Yeah.
It's a Beatles song on Abbey Road.
Oh,
Of all albums.
I listened to a lot of Beatles.
Oh,
Got some weird
Really
stuff.
listens to the June Bugs.
So this is a +4 charge and a +1 charge, I think. Yeah. This is a +4 charge and a -1 charge. These are actually, keep in mind, Maxwell lived in the 1800s. These are maps of equipotential surfaces that Maxwell calculated by hand and then drew. And then obviously they made a printing press version of them, printed them up. But yeah, and then notice that the other lines are all perpendicular, right? These other lines that he's drawing are perpendicular to the equipotential lines. Those are lines along the electric field. Those are the electric field lines. Notice that the electric field lines are always perpendicular to the equipotential surfaces. Notice that this equipotential surface actually crosses over itself, right? Which is interesting. That's the point where there's zero potential energy, right? Essentially zero potential energy. It's not going to roll downhill or uphill at that point because it's at the same potential in any direction. And that's because these two guys are both pushing them. Any potential charge that you were to put there with the same force. It's closer to the smaller charge, obviously. So yeah, these were actually done literally by Maxwell. I think they were traced over in a little more detail by Mr. Lewin, Walter Lewin, MIT. That's where I actually got these from. And notice how there's blue equipotentials around this one, and that's just because they've become negative, right? Those are negative equipotential lines. So pretty interesting historical concept. Notice here, though, any equipotential surface I draw is perpendicular to the field lines. At every point, it's perpendicular to field lines. We know charges move along field lines, or they feel forces along the field lines. And so if I have an equipotential surface, charges will not move spontaneously along an equipotential surface because it's at the equal potential. It's not moving downhill. It's just going around the same topographic line. So they have to be perpendicular. We used to do a lab back in the days, years ago before COVID. We used to do a lab where we actually mapped equipotential surfaces or lines using just a little apparatus. Maybe I'll show it to you. Maybe I'll try to find a virtual lab where we can do that.
That makes sense though, what you were saying. Like the perpendicular thing.
Yeah, yeah. It's like when you look at a topo map,
Yeah.
right? What's the direction of the force on an object that you put there that's free to roll? It's going to be down the hill, right? Perpendicular to the the line of equal gravitational potential yet. All right, sorry about the scattered nature of today. I blame the horrible human being that left the cat there at the entrance.
I think you were gonna say Trent.
No, Trent's all right. He's okay.
I blame Trent. Oh wait. Yeah.
Voltaic beans. Listen, we got by COVID. All right, take it easy, guys.
If you want to.
Charge on the COVID.
See you guys. Thanks for joining. What am I hearing?
Staying
Playing the guitar.
Maxwell's Silver Hammer, dude. It's one of my favorite Beatles songs.
Well,
I'm contacting your parents.
no.
I'm telling them I'm very disappointed by your performance today.
Conference. Your son does not know.
My favorite Beatles song. That is unacceptable.
Wait, do you need
Oh,
me
no,
to
I
come
thought
in
Trent was dead.
to take the test?
You can do it during class tomorrow if you'd rather.
Yeah. Okay, I can do that.
Okay, that's fine.
We're gonna
Thank you.
file that.
Yeah.
You know the drill. Have a good day if you want to.
Okay, you too.